As another example, we can look at D4 and try to compute all its irreducible representations. Here we have to remember the conjugacy classes of D4. There was E and the 180-degree rotation. These were both in the center of D4. This is a calculation we did earlier in the semester when we studied the class equation. And then the remaining two classes were R and R cubed and SR and SR cubed. So there are four conjugacy classes, and therefore there are four irreducible representations. Which is good because we've tried discussing discussing representations of the dihedral group already. And so we can look at the one-dimensional representations first, and we had already discussed them. There was the one that sends r to -1. Well, I mean, there's the trivial representation always. Phi1's the trivial one. Then there's Phi2, which sent r to -1, and s to 1. We saw that that one was in fact a representation. Likewise, was the representation that sent r to 1 and s to -1. And finally, there was the representation that sent r and s both to -1. And then for other group elements, you could figure out the value by the fact that it has to be a homomorphism. So the values are determined by the generators. These are the generators. And in order to make sure it actually works correctly, you just had to check that phi to the whatever r to the fourth actually was always 1, which is the same thing as s squared. And that phi to r SR was also the identity. If it satisfied those properties, then it actually ended up being a group homomorphism. Oh, and these should be 3's, right? This should be 3. This should be 4. These are distinct representations. So there's 4 representations. But I'm missing an equivalence class. Oh yes, S and SR squared. So there are 5 conjugacy classes, so there should be 5 representations. The 4 we have so far have dimension 1. So we're missing 1. So some k squared. And that has to add up to 8, the order of the group. So we see k squared has to be 4. So the remaining irreducible representation has dimension 2. So we can set up our character table with the information we have, the value of the trivial representation on R, S, and SR, and the value of each of those homomorphisms. Right, one sent R to -1 and S to 1. It sends SR to -1. It sends R to 1 and S to -1. It sends the product to -1. So the character table here is very easy to write down. Then you're just stuck with this remaining row. But you know that you've got an orthonormal basis, so the inner product of this row with any of the other rows has to be 0. And I'm going to ignore the dividing by 8 business because, well, you're setting it equal to 0, so multiply through by 8 and you still have 0. Alright, so on this one, all we have to do is take the inner products and realize that the inner products are all 0 of any 2 rows. So if we take the inner product of the first row and the last row, we're going to see that dividing through by the order of the group, which is 8, we're going to have 2 times 1 plus a times 1 plus b times 1, but there's 2 copies of this term because there's 2 group elements here. There's 2 group elements here, so there's 2 copies of this term as well, so 2c and 2d. That has to be equal to 0. I'm just going to keep doing, all these terms are going to have a 1/8 in front. Next up, you also have 2 plus a minus 2b, because there's a negative 1, plus 2c minus 2d equals 0, all times 1/8. The next equation is 1/8 times 2 plus a plus 2b minus 2c minus 2d. And finally, 2 plus a minus 2b minus 2c plus 2d. All that's equal to 0. So to make life easier, multiply through by 1/8. Move the constant term to the other side as a negative 2, and rewrite as a matrix equation. Our coefficients of a are all 1. Our coefficients of b are either 2 or negative 2. Our coefficients of c are 2's, followed by negative 2's. And then our coefficients of d are like this. Times a, b, c, d is equal to negative 2's only. So our ability to solve this 4th character row in the character table, or 5th row in the character table, corresponds to a linear algebra problem. Can you solve this matrix equation? It has a unique solution, and the unique solution is, well, I'll just write it up here. It ends up being a is negative 2, and all the other entries are 0. So none of this other stuff even matters. 2 times 2 plus negative 2 is always 0. So congratulations, we found our 5th character. And so that's 5 linearly independent vectors. That's a basis. And so we now have 5 irreducible representations. And so I'm able to get the character table for D8. And so even though I don't know what this representation is yet, I know its character. In fact, it's not that hard to figure out what the representation is in this case, because you know whatever it does to R and S, it has to send R to something of trace 0 and S to something of trace 0. If you remember, our 2-dimensional representation of the dihedral group was this one. This is a cosine of pi, a cosine of an angle, sine of an angle, negative sine of an angle, cosine of an angle. Here the angle is 90-degree rotation, so the cosine values are 0 and the sine values are 1. And phi phi of S is the reflection matrix, which was this one. These both have trace 0. This does define a representation. You can see the representation has the correct character, and so that tells you that this one is irreducible. In general, it turns out this standard 2-dimensional representation is irreducible, but that takes a little more effort. You have to show that this representation does not fix any one-dimensional subspace. And while that's easy to prove over R2, we have to remember we're actually working over C2 now, and that's a little bit harder. But it turns out we do have 5 irreducible representations, and we understand them all. Another famous example they like to discuss is the quaternion group. We did discuss the conjugacy classes for the quaternion group as well. You had E and negative 1 were in the center, and then I, negative I, J, negative J, and K, negative K were individual conjugacy classes. There's always the trivial representation that sends everything to 1. So now we have to take stabs in the dark. Let's see what happens if you sent I to negative 1. Well then, clearly negative 1, which is I squared, would have to be 1. So there's no choice there. We see there's no restriction on j yet, so let's just decide to make j equal to negative 1 as well. But then we see that k, which is I times j, has to be 1 in order to be homomorphism. Likewise, we immediately see that phi2 of negative I would have to be negative 1, phi2 of negative j has to be negative 1, and phi2 of negative k has to be 1. So once we pick these two values, all the rest are determined in order to be homomorphism. And this ends up being a homomorphism. One can check that. And so this gives a valid phi2. Notice what we ended up doing. We sent I and j to negative 1, and k ends up being sent to 1. But we could do, that gives the idea that you could do the same trick where you send I to negative 1, but you send k to negative 1, and you send j to 1. And then the negative values just get sent to the same thing as the positive values. This also defines a well-defined homomorphism. In some sense, what we're doing here is we're taking Q8 and we're sending it to the Klein 4 group. And then we're looking at representations of the Klein 4 group instead. And there are 4 representations of the Klein 4 group. The one that sends everything to 1, the one that sends one of the elements to negative 1, the other element to negative 1, and the third one, which has to be the sum of the first two, has to be 1. And so that gives us Q4 of I is 1, Q4 of j is negative 1, Q4 of k is negative 1. So from this homomorphism, we get 4 one-dimensional representations of Q8. But there are 5 conjugacy classes, so the remaining one has to be 2-dimensional. So here's our table so far. Here are 5 conjugacy classes. Here are 4 characters of 1 dimension, and here's our 1 remaining unknown character. By now this should look familiar. If you look at the previous example, it's the exact same table. So by linear algebra considerations, it's going to have the exact same entries. And so it turns out the character table, ignoring the labels on the columns, the character table for Q8 is the same character table as D8. D4. And so this is an important example to note that groups are not determined by their character tables. Non-isomorphic groups might have the same character table. You actually need to know the column information. But of course, knowing the column information requires knowing the structure of the group. So that's it. There's an introduction for characters and how to compute some character tables for small groups. That should help you with some of the homework, and some of the other facts about characters and the fact that they form an orthonormal basis should help with other homework. The remaining videos will be focused on understanding why those theorems are true.